So today I want to talk about this problem, minimum pair removal to sort array. This is a hard problem due to the constraints given. We'll get to that in a minute. Uh, s- there is a easy problem, minimum pair removal to sort array 1 with the smaller constraints. So you can just brute force this. We'll talk about that. And let's dive into it. So given an array nums, you can perform the following operation any number of times. Select the adjacent pair with the minimum sum in nums. If multiple such pairs exist, choose the leftmost one. Replace the pair with their sum. Return the minimum number of operations needed to make the array non-decreasing. Okay, so suppose let's take their input first sample case. So as we can see, this is not sorted, right? So what you gotta do is choose adjacent pairs with minimum sum and then combine them until the array is sorted. So what do I mean by that? It's so the sum first pair sum is 7, second pair sum is 5, then 4. The minimum sum in this case is 4, which comes from these two elements, right? So in the first step, they've just combined it and replaced it with their sum, right? So it's 5 to 4 now. You can again see it's not sorted. So you take 5, 2, that's 7, 6. So 6 is minimum. So you combine them as well. And once you do that, this array is sorted. So you did that operation 2 times. So the answer, the output is 2. In this case, the array was sorted, so the output was 0. Now, just keep a look on these constraints. So, we'll talk about what happens if we try to brute force this and how we can come to a very optimal approach. So, yeah, let's get into the explanation. Okay, so firstly, how would you brute force this? Um, given some array like this, uh, there are two steps involved in this. So if you run a while loop, while true, at the starting you check if is sorted nums, then you break from this, right? Otherwise, for I equal to 1 to 0 to n minus 1, or probably n minus 2, you get the sum of uh, the adjacent pairs. So nums I plus nums I plus 1, right? And uh, at each point, you check if this was the minimum. So outside this is int max. So you check if this is the minimum sum that you're getting so far. Sum. If it is, you also keep track of the I where this minimum sum occurred. So if you can move this to an if condition. So if res is greater than sum, you'll have I equal to um, idx equal to I and res equal to sum, right? Then you combine it. You combined it in Java. You can like use the dot set and dot remove. So you remove certain. So if the input was 5, 2, 3, 1, you found the minimum sum here. So you would set this to be the sum. So dot set on this index to be 4, and then remove this element, right? Dot remove this. So now few things to notice. This part over here is O of n, right? This part is again O of n. The remove set again is O of n, right? Now, how many times can this while loop run? It can run basically if you had to reduce all the elements in the array to size 1. So basically n minus one time. So let's take an example where, okay, and one more thing. Once you do that, you increase the number of ops needed and you check again. If it is sorted, you break and then you return ops. So yeah, suppose the array was this, right? 5, 3, 1. So you would first choose this, break it down to 5, 4, reduce it to 5, 4. It's still not sorted, so reduce this to 9. So maximum ops that can happen in such a case would be n minus 1. So worst case scenario, this while loop, outer while loop runs n minus 1 times, giving you the overall time complexity to be O of n square. Now we need to check the constraints. This is obviously not possible. And this is the reason this is a hard problem because you have to figure out a way to do this whole process in a more efficient manner, right? Now, let's break it down part by part. This part can be removed. Uh, so this if is sorted, this could be another function. Like in a brute force solution, this is sorted as a function where you just check if numxi uh, lesser than numxi plus 1, right? So, and if it is the case, you return false or probably greater. Yeah, so in this case, you do this for O of n time. There is an easy way to take care of this. And what is that? You just, in the beginning, uh, you just keep track of how many violations or breaking points are there. So given an array 5, 3, 1, you know this part is a violation because this is greater than this. So you have violation plus plus. In the beginning, v equal to 0. So violation was 0. You checked once. This is not in the correct order, so you increase the violation to 1. Again, for this, you check the condition is true. There is a violation, so v becomes 2. Now you have v equal to 2. So you can just remove this part and run this loop till v equal to v not equal to 0, right? You want 0 violations in the whole array. And once you're doing this remove and set operation, you just need to keep track of when you removed something, did it violate the thing? So, for example, in this case, 5231, right? So first you removed this. So in this case, you saw 3 was greater than 1. So there was a violation in this case. When you combined it, when you reduced these two indexes to one index of the value 4, you removed a violation. So in this case, you do v minus minus, right? Now, suppose there was another one. Let's Now this is for remove case, right? This is for remove case. Now what happens with the set case? So if there was something like 4, 1, and 5, or 6, 1, 5, and you removed this, you combined it into one index with 7 value. Okay, earlier with this element there was no violation, but when you reduced it to 7, right, you can actually take a better case because this is not correct because you need to reduce only the minimum sum. In this case, the minimum sum would be this. But just for the idea, when you reduce it to 7, you decrease one violation for sure here while decreasing it. But in this case, there was no violation. But when 7, 5 got into the array, now there's a new violation involved. So in this case, you'd have to do v plus plus, right? So this part of the solution we can easily keep track of with one variable breaking or violation. and then increase and decrease it. Whenever we either reduce two indexes to one or increase or yeah, so whenever we reduce two indexes to one with their sum, we are either increasing a violation or decreasing a violation. You can keep track of that. We'll come to a concrete implementation of this part later, but that's the general idea and it's easier to maintain. Now, how about this part? How can you keep track of this in something lesser than O of n, right? So it's clearly asking you need min sum. So priority queue should come into your mind, or minimum heap, right? And that would give you something like O of log n, right? And the whole solution would be n log n. And that's acceptable for 10 power 5. So priority queue is the way to go. But now we need to uh, make sure how we use that priority queue to determine this and not use this dot remove dot set and everything gets handled by the priority queue itself. Okay. There are three, four observations to make here. So there are four elements here, right? Now, suppose you chose this index for minimum sum. So 0, 1, 2, 3. These were the indices. And the minimum sum happened with a of 1 plus 2. So this was the minimum sum among a1 plus a2 and a2 plus a3 and a0 plus a1. So this was the minimum sum. Suppose you got that, okay? And now what are you gonna do? And this array was not sorted while you were processing this. So what you would try to do is combine these two indices into one index with their sum. So with a1 plus a2, right? Now, when you do this, what really changes? So and let's denote this by S1, S2, and S0. There's no S3 because there's no further index. So suppose this is the end of the array, right? So S1 basically changed from S1. So this sum changed from A1 plus A2 changed from A1 plus A2 to A1 plus A2 plus A3 because now this is the singular index and the next element is 3. So the adjacent pair is this index and the third index. So in this case, the S1 changed from A1 plus A2 to A1 plus A2 plus A3, right? Also, one more thing to notice now the next index of this one index changed from 2 to 3. So earlier the next from 1 was 2. Now it's 3 because this has been combined into one index, right? That's the second observation. Also, the previous element of 3 changed from 2 to 1, this index, right? Another thing that changed was S0. Earlier, S0 was A0 plus A1. Now, after the reduction process, S0 is basically A0 plus A1 plus A2, right? Because technically, this is the next element now, not A1 and A2, not A1, but A1 plus A2, because this has been reduced. So, keeping in mind all these things, how can we use a queue to keep track of what the next element was? So, what we're trying to do is we're trying to get rid of list.remove, which is an O of n operation, right? List.set. So, like instead of this, what we're trying to do is keep track of next index and the previous index. So we're removing an index, but we're not technically removing it from the array itself. We're just keeping track of what happened, what is the next index and what was the last index. So basically, you're just still removing it, but not in the array itself. So you get rid of these operations. And in the priority queue, you always have the minimum sum at the top. So that O of n reduces to O of log n, right? Now, further implementation details. Uh, so at the beginning, let's run it with an example actually. So okay, this was the case. So how I would go about this is initialize PQ with certain things. Okay, so my PQ or my priority queue or my min heap would be first initialized with all the sums. So it'll have -9, -6, 0, so on and so forth, right? Along with this, I'll keep an ID, not an ID of the index which that sum started from. So in this case, this was 0th, so 0 and 1. -6 was 1 and 2, so 1, 2, so on and so forth, right? And also, I'll keep a, an ID tag. I'll come to this why I'm doing this. Okay. So I'll have an ID associated with each entry into the min heap. So this is 0, 1, 2, 3, 4 until n minus 1, right? And for each at the beginning, for each index, I'll have the last and the next index. So I'll know for 0, next index is 1. For 1, it's 2, 2, 3. This is next. Similarly, for last, I'll have one's last is 0, 2, 1, 3, 2, and so on. Right. So now, how can I build something with the priority queue which gives me a min sum, removes, when you combine two indices, you remove the next one. Okay, so at some point, suppose all these indexes have been removed. Let's not worry about how they got removed. Just for understanding purposes, these indexes were removed. So this is the current I that forms the minimum sum with this J, right? So, and suppose this is K, K plus 1, so on and so forth. In this case, I plus J, A of I plus A of J gave the minimum sum among all the adjacent pairs. So when I combine it, I'm technically changing this to AI of AI plus AJ. I'm removing this because it does not exist anymore. Earlier, next of I was J. So next of I was J. Okay. Last of K was J. So K was this. And next of J was K. Right. This is at some random point in your processing. So when minimum sum, like when the top of the priority queue gave this as the index to reduce, I removed this and I replaced the value of A of I with AI plus AJ. Now, the two things that change. So next of I is now K. So this is how we keep track basically, right? Uh, We're not removing anything, but we're just making sure in a map that we know what the next element and the previous elements are. Next of I becomes K. Last of K changes to I, right? Also, some some of the adjacent pairs, some also change. So now when you polled this, when you got this as the minimum sum, suppose this was I was 9, this was 3. At jth index, the element was 3, this was 9. So you replace 9 with 12, their sum. Also, now there's a possibility of adding uh, what 9, this new sum 12 plus whatever is at k, right? The next of j basically. Next of j is k, right? So at this, now the new sum that needs to be added back into the heap is for further processing is the current sum, whatever we reduced it to. So like it was 9 and 3, so we'll reduce it to 12. So now sum at I will become this sum that we calculated, which got pulled from the heap, plus a of k, right? So this is another possible sum that needs to be added into the heap again for further iteration in the loop, right? So you're running while true, right? So when we reduce this, this is why this is a hard problem because there are too many implementation details to keep track of. Uh, People have done it using doubly linked lists, but that for me made it even more complicated. This is what I could think of intuitively. The time that went into it was on implementation. Okay, so let's get back to it. So you have at a certain point you saw that sum of I, where S is basically adjacent sum. So S of I and I plus one, or S of I and next of I. So S of I got pulled from the heap because this was the minimum. And when you combined it with the next of I, which was J, right? And you somehow remove J. So we're gonna keep an active set where we're gonna just call active of J now becomes false. So we know it's no longer any sum that starts with J, where J is the first element, any adjacent sum is not valid because the index itself is not valid. So anytime you see something on top of the queue which has uh, this as the node that we're processing, we just poll it. We just throw it away. Okay. So going back to it. So I gets reduced to this index gets changed to from a of I to a of I plus a of j. J gets removed. So this also happens. Now, for further processing, a new sum of adjacent of I comes into picture, which is a of I, whatever the new a of I is, plus a of k, right? Where k is the next of j. Secondly, a of last will also change now because a of last was, suppose a of last was previously, or sum of last, basically. Sum of last was last of I. So whatever was available before it, which was not already dead or inactive. So something was here called Z. So S of last of I was previously A of Z plus A of I. This is A of I old, right? But now this got changed to something else. So this sum will also change. If you need to process it in future, this will also change. So reducing any index, any two indices to one changes the previous sum as well. Uh, the current sum for further processing, the previous sum, and the next and last pointers, right? I think this might be getting a little too confusing. Okay, I'll keep trying. So to reiterate, to just drill home the point, you have bunch of indexes. You chose, suppose this for reducing. So you're gonna reduce I and I plus one, right? This is at the beginning of the processing. So nothing has changed till now. You're on operation zero. So S0 was in the queue, S1 was in the queue, S2 was in the queue, S3 was in the queue. So S0 is basically 0 plus 1, A0 plus A1, and similarly. Now, When you r- reduce two and second and third index, the value at S2 at ith index change from AI to AI and AI plus 1, right? This gets inactive. Next of AI gets changed from J or I plus 1 to I plus 2. Last of I plus 2 gets changed from I plus 1 to I plus, oh, sorry, right? Next of I minus 1 does not change because when you reduce, you'll just combine these two indexes and this will act as the second index, 0, 1, 2, right? But in the next time, in the next loop, when you're again processing, so S1 is not valid. The old S1 is not valid anymore because this has been reduced. So S1 has also changed. So I'm gonna not do dot remove. So if I do PQ dot remove, this is again O of K solution, right? So that's why we have lazy removals in priority queues or heaps. So you don't really remove it outright because if it's not on the top, then you can do it in O of 1. But if it's somewhere in middle, you can't, you have to, it'll become a O of K operation. So I'm gonna make use of a lazy removal. So that ID that I talked about earlier, that with each, okay, in the priority queue, I'm gonna enter a sum, which will be the way to compare the current index and an ID. This ID will tell me the latest value that a current node has, like latest ID that the node you're processing has. So if it is an older node, this ID will be less than the current one. So for example, when I added S0, I added it as S0, 0, and 0. Incremented the count, then S1, um, 1, and 1. S2, 2, and 2. Then S3, 3, and 3. This is how I added the elements in the priority queue. Now, when suppose S I told at the ith index, which was 0, 1, 2, second one got picked. So this was the minimum sum. Now, when I want to change these S1 value will change and S2 value will change, right? So when I want to change this, what I'm going to do is add another S1 with the new sum, same index, but with a higher count, 4. So in the next iteration, if this gets to the top, I know this is not valid anymore because S1 has changed and my latest for this node first ID is 4 and not 1. I'll keep track of this latest ID also. So when this happens, I'll just throw it away and in future use this. So this is how I'm planning to use lazy removal. So this way, like you can have all of these things in O of log n time. So the basic idea is very simple. You keep track of the next and last. Okay. So in this case, when you have next, you'll also have next. So basically, when I'm changing something, so I'm saying my S2 was earlier AI plus AI plus 1, right? Now, when these two got combined, so technically now my S2 becomes AI plus AI plus 1 because this got combined into one index plus A of I plus 2. So I need this next also. That I can just get by having, so next of I is J, next of J is something K, right? So next of I is K. So we'll have next information also. So each iteration we'll pick the minimum sum, combine it into one index, change next and last pointers, right? Change this previous sum. So if this was the current node, we'll also have last of I, as something, let's call it A. So SA also will get changed. So if there was, so SA gets changed, uh, SI gets changed, right? And these two pointers get changed. So next of I becomes K, last of K becomes I. So these are the changes that you need to make. Yeah, this is pretty much the idea. Now let's try to code this. Sorry. So in the beginning, I'll just keep a map to keep track of my next 10 last pointers. So this is my last, right? This will show me what? This will be index and the last active. Then I have next, which is another hash map. This will give me index and the next active. So instead of basically removing and setting new values, I'm just keeping track of next and last using maps. Another one, which will give this will I'll call this latest. This is nothing but the ID that I was talking about. So this is for lazy removal. So if I'm adding a new sum, if I'm adding S1, basically S1 in the beginning is A of 1 plus A of 2, right? So if I'm combining it at a certain point, I'll have a new S1 and a new S0 as well. But S0 already exists in the heap. So I wanna mark it as stale, and I'm gonna use this latest to do that. I'm just gonna keep a counter which I'll keep increasing for the newest sums and for the ID. So this is for lazy removal. It'll basically show you index and the latest counter it has. Let's call it counter, right? And another map, I know people can make this much more optimal and cleaner, but at least something to work with. So this is outright removal. So this part of the program is for like new sums being added. So when you reduce two indexes into indices into one, you're technically, so suppose if you choose S1, so A1 was the value at one index, A2 was at second index. So you removed two second index and you change the value at 1 to A1 plus A2. So this is outright removal. So this will just show me if whether an index is active or not. So this is index telling you active or no. Okay. Now, uh, I'll have a node. So what did I say? I said I need a sum. So first of all, I'm gonna keep the sum as a long value because if you see the constraints, if all of them are close to 10 power 9 and you keep reducing, you keep summarizing each value, you're gonna end up with the integer overflow. So this is wrong. And this is the current. Current is just the index. So which index are you processing right now? And also the counter, right? Let's call it ID. You'll have this is just like making your node class to be used in the heap. Okay. So now going to the core logic. Mm, this is length. Count is 0. So this is basically my ID. So each summation that I put in back into the heap, I'm gonna associate with an ID. So that way I know if for that node, for that index, is it the most current submission? If not, then I'll just pop it out. So this count is for that. Operations is technically my answer, and number of violations till now. So right now I'm assuming there are no breaking points, right? We'll change that in a while. Now you have long array. So this is technically for when you change the value. So when you reduce, when you replace a of I with a of I plus a of j, right? The next element. So this is for that array. This is for that. And now you finally have a priority queue, which will have a node in it. So now, okay, uh, we need to find the minimum element, right? Minimum sum, right? So for that, I need to check a dots. If a dot sum not equal to b dot sum, then I can return b dot sum, right? If they're equal, so you need to look at this part of the question. If multiple such pairs exist, choose the leftmost one. So in that case, if it is equal, you just return you can just return this a dot current. So current is basically my ID associated with each node. It's my index. So the leftmost will have a lower value of current, obviously. So A of current and it's B of current, right? Okay, so now what do we need? Now we need to fill our next and last pointers. So that is pretty simple. At the beginning, you'll have, I'll first make all of this long array equal to the nums. Next pointers will be I plus 1, right? All of them are active. All the indices are active. Last is the previous value in the beginning. Now, except for the last index, I can't have a minimum sum associated with it. So S of n minus 1 does not exist because there is no next element, right? So there's no minimum sum. So I'm just gonna, in the latest, I'm gonna put latest I count, right? So for that index, for S0, it is count now, right? The ID is count. So that is the latest sum that we have starting from that index. And yeah, so that's the latest sum that we have. Uh, nums I plus, so in the beginning, each one is active. So it's the next element technically. I, that's the current that we're talking about, and count. And we just increase the count later. Also, we need to check if nums I is greater than nums I plus 1. So you know that's a violation. So this is one of the breaking points. So you increase this breaking point here. Okay. So now we gotta run a loop till breaking gets reduced to 0. So there are no more violations technically, right? Now there is a pruning process here. So that pruning is for what I told you earlier. So there might, I'm doing a lazy removal, and in that case, there might be an active index. So for index 0, uh, there might be two S zeros. So S is basically this plus the next element, right? So when you suppose you have let's say one, two, sorry, one, two, three. So there was one S0 in the beginning, which had a value of 3. So 1 plus 2, 0th element and the next element. But I combined 2 and 3, right? So this became 5. In this case, now S0 is 6, right? Not 3. So for this, the 0 is still an active index, but it's late. The latest value associated with this first sum was count, suppose 1. And now this count is 2, right? So and this 2 will be stored in my latest map saying the value, the count, the ID associated with 0 is 2. And I'm just gonna check if this latest of 0, latest dot get 0, if it's greater than whatever is being processed in the beginning. If it is lesser, then that means this is a dead node, right? So I'm just gonna poll it. So I'm not removing it when it's at the bottom. I'm just pruning it when it's at the top. So I'm gonna do while PQ is empty and so suppose it's a completely dead node. So in the example that I gave right now, so you combine 1 and 2, or there was the index was the array was 1, 2, 3. You combined 2, 3, right? So the third index is gone. So that's a completely dead node. So I can just mark it as active of 3 is false, right? So if active, and you'll actually get an idea of what I'm talking about in a minute. So active of PQ dot peak dot current. If it is inactive, then you gotta poll it, or latest dot get PQ peak current. So the node that you're processing, the index that you're processing, if it has an ID of greater than what the ID of the current node is, then you poll it. You just throw it away. You don't need to do anything with it. Okay, so this is the pruning part. So this is the lazy removal part. You're only removing nodes and the nodes from the heap when they're at the top. Never using pq.remove, which is O of k, or the number of k being the number of elements in the heap. Okay, now you come to a good node, so which actually can be reduced. So first you have node.sum, right? Current, which is the index, and ID, node ID. Now you have the last element, last dot get current, the next element, also the next. So this is nothing but next of next any, right? So you have a track of whatever is active before it and after it. Now what can you do with it? First, few things to notice. Now, if array NE, so we're checking in our long array, right, is less than array of current. What does this mean? So something like 4 and 3. So this is a violation, right? And you're combining these two, right? Because current is the node that has been chosen to be reduced, right? When you reduce this, when this is the case and you reduce it, what's going to happen? A violation is going to go away. So there was a violation here when you reduced it, when you made this part disappear, this index disappear, and this got changed to 7 instead of 4. You reduced a violation. So I'm going to decrement the breaking counter, right? Also, if next is not n, an array of NE is greater than array of NE. Now, what does this mean? So again, there was a violation here also. Suppose this, right? So when you combine these two, first of all, you remove this violation, which is taken care with this part. Now there was another violation where array of NE, this value was greater than this. So there was a violation here also. So this will also get removed. It might arise again, as you'll see, because if you reduce 4, 3, it'll become 7, 2 now. So another violation arose, but we'll take care of that later. But for the time being, when you reduce this, so this violation also got removed, right? So this is again, you decrement it. One last case. If last is not minus 1 and array of last is greater than array of current. So again, a breaking condition got removed. So technically, suppose, for example, this was 5 earlier and you reduce this, it became 572, right? So another violation got reduced. Next, you change the current with the sum, this sum that got pulled, the minimum sum. You change the current value. Now, if this is not n, like there is a next element, so it's basically not the like second last one or the last one, sorry. Like if any is not n, so basically you're not at the end of the array. You'd have latest. So now I'm gonna put the latest value of current. So I'm gonna add this sum, this value, right? Array of current plus array of next. Okay, you'll see it in a while what I'm talking about. Let me write it down. Yeah. So this was for 4. This got reduced to 7, right? And this got removed. 3 got removed. So now the new sum associated with this 4 index, where this element 4 is, that index, now the new sum is 4 plus 3 plus 2. So the sum and the next index, the element at the next index. So this is what I'm doing, right? I'm adding that. And if now to check if a new violation got added. So this is that point. So if array current, so the new value, so this got 4, 3 got reduced to 7, but another 7, 2 is also a violation, right? So I'm checking here, and if the new violation got introduced, so breaking increases. Similarly, you need to change. First, you need to put next as false. So it's not active anymore. It got eaten up. Now, similarly for the last index. So in this case, again, count, right? And you add a new node. Now, the new node's value is array of last plus the present new sum. So the new, this element, current element, the element at the current index got reduced to uh, a of I plus a of I plus 1, right? So sum of last is also now array of LA plus sum rather than array of LA plus array of current and count plus plus. Now again checking the violation if after making array current to the new minimum sum value, if you introduced another violation, then breaking increases by a 1. And in the end, after this, you just change the next counter. So, right? So now next of currents becomes next because next is completely off. And if any not equal to n, last also changes. So any is last becomes current. And you increase the number of ops and you return this value. Yeah, so I think this should work. Pretty slow. I'm pretty sure people can optimize this much more, but it's within the constraints. It's a O of n log n solution. Yeah, so that's pretty much it. Thank you.